Hello, my name is Milena Bobea Graciano. I'm a materials engineer at the Johns Hopkins University Applied Physics Laboratory. I am also a systems integration lead for dust, extreme environments, and simulants for the Lunar Surface Innovation Consortium. An important environment to consider for space hardware is vacuum. The lunar atmosphere is known to be very weak, and it is called an exosphere. It is comprised of noble gases that are released from the lunar interior or result from the solar wind striking lunar surface materials. These gases include hydrogen, helium, argon, and neon, with carbon dioxide products that are released during the solar illumination. When these gases are released, they spread across the lunar surface by bouncing across the surface on ballistic trajectories in a random walk process. Gases can travel several kilometers before experiencing loss mechanisms that remove them from the exosphere. This is why the exosphere of the moon is very tenuous. It is constantly experiencing a weak supply and fast loss of gas particles, leading to an average pressure range of 10 to the minus 13 to 10 to the minus 10 torr. Hardware choices for lunar surface systems need to consider the effects high vacuum can induce on materials. Commonly used materials may not be suitable spaceflight components due to their poor thermal vacuum stability. For example, some metals can sublimate in space vacuum, even at temperatures considerably lower than their melting temperature, such as zinc and cadmium. These can also spontaneously grow whiskers, such as those shown on the right images for tin deposits in electronic devices. These whiskers are capable of causing electrical failures, such as sustained plasma arcing, or produce conductive debris when detached from the plating surface. For this reason, zinc, tin, and cadmium are prohibited materials for space applications. Wet lubricants can also be problematic, as they can travel along hardware surfaces and contaminate sensitive items, such as coatings or optical lenses. Non-metallic materials may possess deleterious outgassing characteristics, such as high total mass loss or high condensable volatile collectible material. Outgassing effects can alter a material sufficiently to impact its dimensions and function, which can affect system performance and lifetime. Cleanliness is another special concern for space vacuum components. Hardware must be free of particulate and molecular contaminants that can cause serious problems, such as those highlighted on this table. Particles on an infrared sensor led to poor signal-to-noise ratio, while those on solar array panels affected power production. Similarly, molecular contaminants can stubbornly adhere to lenses, affecting the function of cameras and optical sensors. Take a look at this example of a silicon rubber seal that was used in Apollo Command Module windows. Because of the high temperatures that are encountered during entry, these multi-pane windows needed insulation. The insulation design included silicon resin impregnated glass fibers bonded with room temperature vulcanized silicon rubber. Additionally, the gasket that was used to surround the heat shield window was made of glass cloth reinforced, heat molded silicon rubber. Soon after Earth orbital insertion, a film appeared on the hatch and side windows of the Apollo 7 and 9 command modules and continued to accumulate during flight. At cold temperatures, the contaminant crystallized and became opaque, limiting visual observations. Chemical analysis of the film revealed that the contaminant was an organosilicon high molecular weight compound. Outgassing tests reveal that the major contributors to this contamination event were the silicon rubbers. As a corrective action, a decision was made to vacuum bake the silicone components prior to installation on the spacecraft. You can see on the bottom right that a rough vacuum bake at 205 degrees Celsius for 48 hours was sufficient to reduce total mass loss and the amount of condensable material for the silicon rubber. The lesson learned led to the use of vacuum-baked parts for all command module windows, a practice that started with Apollo 10. For any spaceflight component, it is imperative to consider the material choices used in its construction and their respective outgassing properties. NASA has a few libraries with this type of information, along with thermal vacuum stability ratings. These include the NASA RP 1124, outgassing data for selecting spacecraft materials, and the Materials and Processes Technical Information System, also known as MAPTIS. As novel components continue to be developed for lunar surface systems, it will prove important to test their respective outgassing behavior. Several standards are commonly used for this type of evaluation, including the American Society for Testing and Material Standards, or ASTM, E595. In this test, the test article is subjected to a 24-hour soak at 125 C in a high vacuum chamber, and then measured for total mass loss and collected volatile condensable material. In fact, NASA's outgassing criteria for thermal vacuum stability demands a total mass loss of less than 1% and for the collected volatile condensable material to be less than 0.1%. Similarly, the ASTM E1559 is an outgassing test that varies in soak temperature, which can be more informative for specific target thermal conditions. This test measures outgassing rates over time and desorption kinetics. For contamination-sensitive optical surfaces, the Marshall Spaceflight Center specification 1443 provides guidance to test non-metallic materials and evaluate their potential to become a threat to function. Many materials may have as-per-cured conditions that are unacceptable for flight use. For this reason, there are cleaning and outgassing protocols that can be established for contamination control. Precision cleaning, inspection to cleanliness levels, handling rules, and environmental regulations are some examples of this type of control program. For components that have unacceptably high outgassing characteristics, such as the Apollo rubber seals, vacuum bakeouts may be needed to reduce their outgassing potential in their next higher assembly. For very contamination-sensitive systems, you might need to engineer for their protection with the use of molecular adsorbers, covers, and purge systems. And finally, consider all hardware and their contamination potential in your performance design margins. Thanks for watching, and I hope this module on vacuum has been informative.